the track 3, first session of the day. We're going to start today. My name is Patrick Flaherty, and I'm at the University of Massachusetts Amherst. And we're going to start with 5 spotlight presentations, and then we have our oral talk, and then we end with 5 more spotlight presentations. Let me we'll start right now with the spotlight presentations, and first up we have Dennis Way.
Good morning, everyone. So this work is on binary classification using Boolean rules, either disjunctive normal form or conjunctive normal form. So here I'm showing 2 simple examples of DNF rules. Our motivation in considering, or I should say revisiting this class of models, is because they're directly interpretable by humans, and thus they help address the growing need for interpretability. This is true so long as these rules have not too many clauses and not too many conditions per clause. So there's this trade-off between rule simplicity and classification accuracy that we seek to optimize using integer programming. These Boolean rules are closely related to other classes of interpretable models. In particular, a DNF rule is the same as a decision rule set, and the rules are not ordered as they would be in a decision list. Note also that the complexity of a model depends on its representation. So before I get farther, I'd like to get one preliminary out of the way, which is to assume that all features that are not binary have been binarized, either through one-hot coding or through thresholding. So with this assumption, then, the main difficulty in learning such Boolean rules is that the number of possible clauses, say conjunctions in a DNF, is exponentially large. A clause might involve a single feature, 2 features, 3 features, and so forth. So previous works, by and large, have limited the search space using heuristics. And moreover, these heuristics may depend on criteria that are not directly connected to the classification task. So in contrast, we are able to consider all possible clauses using the technique of column generation. So conceptually, the master problem we're solving is to select an optimal subset of clauses from this exponentially large set, which I'm representing here as columns of a matrix. Now, obviously, we can't enumerate all of these candidates, so what we do instead is we have to solve restricted versions of this master problem, restricted to small subsets of columns. After solving each restricted problem, we have to check whether any of the columns we've left out can potentially improve the solution. So the key question is, can this check be done tractably? In our case, we are able to formulate this check as what we call a pricing IP. The key point being that this pricing IP no longer has an exponential number of columns. Right? It is still an IP, but it's relatively benign. It's similar to a set covering problem. We also use a heuristic along with IP to generate improving columns. The difference from some other heuristics is that this one is optimizing the correct objective guided by this pricing IP. So the algorithm then is to alternate between these 2 steps, generate improving columns, and then resolve this restricted master problem with the new columns. To solve the IPs, we use the solver Cplex. For the results that we've reported in the paper, we've limited the time of this overall procedure to 5 minutes. And that was in part to show that IP is still viable under such limits. Once this procedure terminates, since we're using IP, we can get various optimality and near optimality guarantees that we'd be happy to walk you through later at our poster. So the first numerical evaluation that we did looks at this trade-off that I mentioned between classification accuracy and rule complexity. Here we're comparing against some recent methods that also address this trade-off, and we find that our column generation, the ones in blue, dominate this trade-off in at least half of the data sets that we tried. So for our second evaluation, this is a more traditional task. So here we seek to maximize the accuracy by tuning the complexity parameters. Here what we find is that column generation is very competitive with existing methods that are designed to maximize accuracy without much regard for complexity. And indeed, on some of these data sets, we find rules that are equally accurate, but much simpler. So to sum up, our work is on Boolean rules that are both interpretable and accurate classifiers. Our key insight is to use column generation to search this space of rules effectively and comprehensively. And I invite you to come to our poster number is 79, downstairs on the second floor at 10:45 today. Thank you.
Good morning, everyone. I'm Kaito Fuji from University of Tokyo, and this is joint work with Task Soma. In this paper, we propose fast greedy algorithms for dictionary selection with generalized sparsity constraints. First, I would like to explain what is a dictionary. Let me cut this image into small patches like this. Then it is natural to consider these patches are generated from some patterns. A dictionary is a collection of such patterns. If we have a good dictionary, we can give a sparse representation of each patch. In other words, each patch can be expressed as a linear combination of a few atoms selected from the dictionary. Dictionary selection is an approach to learning a dictionary from data. In dictionary selection, first, we prepare several existing dictionaries designed in signal processing research. Out of the union of these dictionaries, we select several atoms as a dictionary. While selecting dictionaries, we must consider giving a sparse representation of each patch. By regarding a dictionary as X and a set of atoms for each patch as ZT, we can say this problem is a two-stage set function optimization problem. We consider a generalized version of dictionary selection in this paper. The formal statement can be written like this. The first maximization corresponds to selecting a set of atoms as a dictionary. The second maximization corresponds to selecting a subset of a dictionary for a sparse representation of each patch. Here we consider a generalized sparsity constraints. With this generalized sparsity constraint, we can utilize prior information about the dataset. Ft is a set function representing the quality of Zt for each patch. This is the problem we tackle in this study. Our contributions are twofold. The first contribution is replacement OMP, which is a fast greedy algorithm for dictionary selection with approximation ratio guarantee. The second contribution is p-replacement sparsity families, which is a novel class of sparsity constraints generalizing existing ones. The starting point of replacement OMP is replacement greedy algorithm, which was originally proposed for two-stage submodular maximization. This is a similar but different problem. First, we apply it to dictionary selection and obtain an approximation ratio guarantee, but this is too slow to apply to real datasets. So we accelerate this method by introducing the concept of orthogonal matching pursuit and obtain replacement OMP. In comparison to existing methods for dictionary selection, replacement OMP is based in three aspects: approximation ratio, running time, and empirical performance. Our second contribution is p-replacement sparsity families. There are several sparsity families proposed in previous work. We generalize them by introducing a novel class called p-replacement sparsity families parameterized by p, like this. We also extend replacement OMP to this generalized sparsity constraints and gave an approximation ratio guarantee. In summary, we propose replacement OMP and P-replacement sparsity families. We also empirically compare dictionary selection methods with dictionary learning methods and extend the algorithms to online dictionary selection. If you are interested, please come to our poster. Thank you for listening.
Hello everyone, I'm Xiangyu Guo from University at Buffalo. This is my joint work with Shili. The title of my work is Distributed K-clustering with Heavy Noise. So first, let me define our problem. Suppose you are given a huge dataset P of size n distributed over m different servers. And here we are assuming the MapReduce model, which means there is additional server as the coordinator, and we only allow communication between the coordinator and the servers. So the task is to conduct a partial clustering. Namely, you are allowed to remove part of the data set, say no more than z points, which will be called outliers. And we want to find a good clustering over the remaining non-outliers. And here we want to cluster it into K clusters, and that's why we call our problem a KZ clustering problem. So the task is really twofold. You need to choose points, or you need to choose outliers to be discarded, and you need to find a good clustering, just as the traditional clustering problems. So we are mainly concerned about two aspects. First is the clustering quality. Just as in the traditional clustering problems, we want our algorithm to achieve a constant approximation, which means the objective is no more than constant times optimal cost objective. And since we are in a distributed setting, we want our algorithm to have small communication cost, since in this setting, the communication cost often becomes performance bottleneck. In particular, we focus on the case when data is believed to be highly noisy, which means the number z is huge. So our motivating question is, can we achieve constant approximation with communication cost much less than z? Unfortunately, the answer is no. We can prove a lower bound, saying that any constant approximation algorithm needs communication cost at least the order of z. But if we step back a little bit and allow approximation over another dimension, say we allow removing slightly more than z outliers, then we can indeed achieve constant approximation with small communication cost. So our results, our first result is for the KZ center problem. In this problem, the objective is to minimize the maximum distance from each point to its nearest center. And in this problem, we achieve constant approximation in terms of the objective, and we only remove 1 plus epsilon z outliers. And our communication cost is independent of z. Our second result is for the KZ median and KZ means problem. And in this problem, we achieve 1 plus epsilon and 1 plus epsilon approximation ratio in both, in both aspects. And the communication cost is also independent of z. But here, to achieve 1 plus epsilon approximation ratio in the objective, you may need exponential running times. But in practice, this is not a big problem, because you can simply replace the exponential part with the common heuristic methods, such as the Lois method. So if you are interested in details, our poster will be number 73. Thank you.
Hello, I'm Amin Karbasi from Yale University. Today I'm going to talk about streaming submodular maximization, which is a joint work with Moran Feldman from Open University of Israel and Ehsan Kazemi, my postdoc at Yale, who couldn't be here due to visa issues. So one of the main applications of submodularity is in data summarization, when we have a huge data set and we would like to find a representative subset of data points. That might be a large data set of images in which we would like to find a diverse subset of images, or it might be a data set of sensor data where we would like to find informative data points. So in all those applications, the utility function usually shows diminishing returns, which means that for a given data set or ground set V, a set function f is going to be submodular, it's going to show diminishing returns if for any two sets A and B, where A is a subset of B, and for any new element x, adding this element x to the smaller context A has a larger marginal contribution than adding it to the larger context B. However, very often in practice, we would like to solve this problem at scale, either because the data points come at a very fast pace, or we don't have time to read the data set more than once, or we may not even have random access because the data set is very large and we can only read a small patch of data points at any given point of time. So we like to have streaming algorithms. And here, Ehsan had a very nice animation that we had a clip, and our algorithm will basically pick a diverse set of frames from the clip. I think he's going to be doubly sad now because I cannot run it in a PDF. So the key challenge is to extract a small representative subset out of a massive data stream on the fly. And formally, we have a submodular function f, and we would like to find a subset S that maximizes this submodular function. And in our paper, we assume that the function is non-negative, but it may or may not be monotone. And we also consider a very general set of constraints, which we call, which are called p-matroid, which can model all sorts of constraints that you can see in practice. So more formally, a p-matroid is basically a set system where we have m metroids, and each element of the ground set can appear at most p times in each of the metroids. And as special cases, it contains the cardinality constraint, partition metroid, intersectional metroid, etc., etc. And we propose a very simple algorithm, which we call sample streaming, but it does something very counterintuitive in the first phase. When an element arrives, it discards that element with probability 1 minus q. It doesn't even look at the element. Otherwise, it's going to check which element it has to remove from its current solution in order to be able to add this new element and maintain feasibility. And finally, it's going to accept the element, it's going to add it to the solution if the marginal gain is above a threshold. So having a subsampling algorithm has two advantages. First of all, it makes the algorithm fast. Second, we prove that if you do the subsampling correctly, you can actually transfer any algorithm that works for the monotone case into an algorithm that works for the non-monotone case, but it has also a disadvantage that we might actually lose in terms of utility that's provided by the algorithm. So what we could prove is that if we set the parameters correctly, namely the parameter of acceptance of an element and the threshold, then this simple algorithm provides a constant factor approximation. In particular, in the non-monotone case, the constant factor approximation is roughly 4 times p plus 2, and in the monotone case, it is 4 times p. So if we compare our algorithm to the previous art, we provide a solution for the general non-monotone submodular maximization subject to a p-matroid constraint, where it has the tightest approximation guarantee, it requires the minimum memory, and the fewest queries per element. And if you are interested in our work, please come to a poster, I guess, on the second floor. Thank you.
Now we have our oral presentation, and for that we have Joshua Wong.
All right, guys, thanks for coming to my talk. So I'm going to talk about maximizing some modular functions, and this is joint work with Rad Niazadeh, who's on the job market this year, and my PhD advisor, Tim Roughgarden. So I'm going to review the more formal definition of submodularity in a couple of slides, but let me first develop your intuition with a more concrete example. So in this example, let's imagine that we're an advertiser and we have access to a couple of platforms that we want to advertise on. In this picture, we have access to newspaper ads, TV ads, and internet ads. And naturally, one very natural objective for us as an advertiser is to maximize the revenue that we get from reaching additional users minus the cost of advertising on each of these platforms. And the interesting thing in this example is that the different platforms have overlapping user bases. So for example, if I take out ads on the TV platform in the middle, I'll reach the user, the person in the middle. But if I later decide to take out ads on the internet, they won't be as effective as they would if I had just taken them out to begin with, because I've already reached some of the internet population. And the one thing I want to note is that this function is not monotone because it's possible that, as I choose to advertise on something, the cost outweighs my additional revenue. All right, so this example falls under the umbrella of submodularity. So you guys are probably, you've been hearing a lot of submodularity. Well, the basic gist of submodularity is that it's just trying to capture this idea of diminishing returns. As you choose more things, each thing becomes less effective. So the classical notion of submodularity is about discrete functions. So, our functions have a feasible region which corresponds to the vertices of a hypercube. So back to our advertiser example on the previous slide, 3 platforms would correspond with a 3-dimensional hypercube. And for example, the second coordinate of the hypercube will be a 1 if we choose to advertise on TV and a 0 otherwise. And we'll say that such a function is submodular if, as you increase one of the coordinates from 0 to 1, any future increase of a different coordinate becomes less valuable. So that's exactly our diminishing returns intuition. So this notion is nice for us because it has 2 important properties. So the first is that it covers a lot of important functions. From a variety of areas, including TCS, economics, optimization, and machine learning. And the other thing is that this definition is still strong enough for us to reason about theoretical algorithms for it. So there's a rich literature that covers many different cases. For today, for this talk, the case that we'll focus on is the case where our function is non-monotone. We're trying to maximize it, and there's no additional constraints on our feasible region. So the small tweak that we will have to the standard discrete submodularity model is something called continuous submodularity. So the research trend in recent years is, we have this very nicely developed toolkit of ideas and techniques for discrete submodularity. We'd like to apply it to a larger set of functions. And in this case, we'd like to apply it to continuous functions. So now, we're no longer, the feasible region is no longer just the vertices of the hypercube, it's the entire interior region of the hypercube. And we're gonna have to redefine submodularity, so what should submodularity be? So if you look at our previous definition, the natural extension of that would be as you increase one of the coordinate values, as you increase xi, all of the other partial derivatives, df over dxj, begin to shrink. And what the discrete definition leaves open in this continuous setting is what should happen to df over dxi. So if you insist on the most bare bones mathematical interpretation of the previous definitions, what you're going to get is no additional guarantees in one dimension. And for the purpose of the talk, we'll call this continuous submodularity. On the other hand, you might decide to continue going with this idea of diminishing returns, and you might say, oh, as you increase the value of xi, the function will look concave. It's not as good as you keep increasing it. And that's a stronger condition, so for the purposes of this talk, we'll call it strong continuous submodularity. So we have a weaker condition, and we have a stronger condition. And as an example of why generalizing from discrete to continuous might help us, 2 example applications for machine learning are pose estimation and recommender systems. All right, so now let's talk about what is the current set of discrete submodular results, because like I said, we're using our discrete submodularity understanding to help inform our understanding of continuous submodularity. So obviously this is not all the results, but the 2 landmark results for our setting The first one is Lower Bound by Feige, Mirokani, and Vondrak in 2011, and they show that information theoretically, you can't hope to do better than a 1/2 approximation. And the nice thing is that this is matched by an algorithm in 2015. So Buchbinder, Feldman, Nauer, and Schwartz showed that there was a 1/2 approximation algorithm. This algorithm is commonly known as the double greedy algorithm, and it'll serve as the basis for our continuous algorithms. And the thing I want to note about the lower bound is that the lower bound also precludes better approximation algorithms for continuous modularity. So, at this point, the best thing we could hope for is 1/2 approximations for continuous modularity and strong continuous modularity. All right, so let's see the current state of the art before our work. So the best continuous modular algorithm is a 1/3 approximation given by Bien et al. Just last year. And the best, so if you know a little more, if you know that each dimension looks concave, then there's an algorithm by Soma and Yoshida that shows you can get that 1/2 approximation. And so what do we show for these two settings? Well, for the continuous case, we managed to improve the approximation ratio from 1/3 to the best possible 1/2. So at this point, we really are in like the best possible world. We managed to match that discrete submodularity lower bound. And also, so obviously for the strong continuous case, we can't improve the approximation ratio any further, but if you do have this additional assumption about your function, we show that you can get a very fast algorithm. There's a near linear algorithm that gets a 1/2 approximation. So I'm going to drill down a little more into these two results. All right, so the first one, we have f. You have the bare bones continuous modular assumption, and we'll also have the assumption that this function is L Lipschitz. And we provide a randomized algorithm that runs in roughly quadratic time and returns a point that's a 1/2 approximation minus an additive factor of epsilon. So what I do want to mention is that this L Lipschitz continuity assumption is in fact necessary. So if you think about f, just think about a one-dimensional function f, the continuous modularity assumption actually gives no restrictions on what f could be. So you do need something additional to maximize an arbitrary one-dimensional function. And previous work has to do similar kinds of things. Okay, so let's talk a bit about what exactly this algorithm looks like. Okay, so like I said, we rely on this double greedy framework of Buchbinder et al. What is that double greedy framework? Well, the key idea is this. So we have 2 points. They start at the all zeros vector and the all ones vector. And all we're trying to do is we're trying to make these 2 points agree completely in every single coordinate. So we just go over the coordinates in arbitrary order, and we assign them the same value for that coordinate. At the end of the day, they have the same point, and we'll choose that point. And how exactly do we choose the coordinate value? Well, it turns out for our continuous case, what we show, we do the theoretical legwork to show that this boils down to solving a zero-sum game. So the algorithm is sort of one player in a zero-sum two-player game. And what does that look like, at the end when you have to actually implement it? So I'm going to show you the main steps to convince you we're not doing anything too crazy. This is something you could actually implement, but I don't expect you to immediately grasp why all these pieces are here. So first of all, we use a pre-processing step based on the 1/3 algorithm of Bien et al. And we use the 2 current points, x and y, to derive 2 marginal value functions that say, if I choose z as my current value, how much is the value of x going to improve and how much is the value of y going to improve? So if we look at these 2 functions, they trace out a curve in 2 dimensions as I vary z between 0 and 1. And then we do some geometry. So we show that you can compute the 2D convex hull of the curve, you can compute an intersection, and you can wind up randomly choosing a point on the original curve, and we'll set both xi and yi to the z value that corresponds to the point that we chose. And if you go through the analysis, this gives you a 1/2 approximation. All right, and I'll also talk about our other algorithm. So in this case, f is strong continuous modular. So in every coordinate, it's concave. And we also assume it's Lipschitz. So we show that there's a near linear time algorithm that essentially gets the same guarantee. And the idea behind this algorithm is, so in the previous algorithm, we were using this double greedy framework. Our subroutine for each coordinate was we were solving some zero-sum game. For this algorithm, we actually give a binary search condition. So we search for z extremely quickly, right? We just, break the interval in half and keep doing that. And this improves the previous best algorithm, this Somo Yoshida 2007 work, by more than a 1/epsilon factor in running time. So if you think about it, if you want your final result to be accurate within 1%, this represents a 100x speed up in the theoretical bound. Okay, and I'll talk a bit about implementation. So we actually implemented the code ourselves in Python. You can find it at this link. And the key thing I want to note is that, I mentioned when going through the algorithm quickly that you have to compute this 2D convex hull. Actually, you can do that with something called a gram scan, and you can do even better than the basic gram scan. Because of properties of continuous submodularity, you can avoid the need to sort. So it's a very fast subroutine. Right, so for our experiments, we tried to replicate the experiments from the previous best work. That's this Bien et al. Paper. So we have synthetic data. We test things on dimension 100. And for each column of this table, the 3 functions are being given the same 20 random functions that were generated. And as you can see, they have roughly comparable results on the synthetic data. And the key point is that our algorithms are backed by a stronger theoretical guarantee. For future directions, there's a lot of future directions, as you can see by this session on submodular optimization. So one natural thing is, we were optimizing over the entire hypercube. Can you optimize when you have additional constraints, like downwards closed constraints? There's a special case. So we were doing non-monotone. Can you do monotone under cardinality constraints? There's work being done on parallel algorithms. So as you can see, our algorithm is very sequential. We have to go coordinate by coordinate. And also, can you do this stuff online? Can you learn these functions as you go? Maybe you don't know what revenue you'll get from these various advertising sources. All right, here's a recap. We're at poster 76 downstairs, and I'm open for questions.
All right, if you have any questions, then make your way to the front. We have a couple of microphones here for you. Let me just give a minute for people to make their way up if they have a question. Okay, while that happens, I guess I'll start things off. We have a question right here.
Oh, okay.
Right. So just something about one of the questions. So, right, the parallel algorithms have been done, right?
Yeah, so there's work on parallel algorithms, but as far as I know, I don't know that they're tight. So I think there was a poster yesterday about it where they improved.
No, it has been done a month ago.
Oh, sorry, say that again?
It has been done a month ago, the parallel algorithm.
Yes, but they got it down to log n squared rounds, is my understanding.
There is no. Okay, we can talk about it later. Yes.
Yeah.
So I guess I have a couple of, I was interested in the application to recommendation systems and things like that, because kind of moving from discrete to continuous kind of opens up this wide range of domain problems and things like that. Yeah. So have you tried this out on any of those types of applications, or have you looked at that?
Right. So I should say, so from the examples, okay, so the DPP softmax set of examples is actually based on the kinds of functions you would get from these two applications. So it boils down to solving some DPP. You're trying to maximize the most likely point, and then to do that in the continuous setting, you take the softmax extension. So that's exactly what this last column is. Obviously, the experiment we wish we had the data to run is take the actual examples and then convert them into the functions.
I guess I have one more question. So at the beginning of your presentation, you showed very nicely that there's this limit, and if you achieve the limit, then kind of you're done. So is there more to be done in this area, or is the next step to kind of move outside of this area? Have we achieved kind of have we solved this problem, or is there more to be done in this problem?
Sure. I think what is important to understand is, so the limit is against the theoretical best thing you could prove about your algorithm. I think oftentimes, when you're testing on practical data, you can hope to do much better than 1/2. So, if you have data, you can run more experiments. I think there are other algorithms to definitely try. So I know Bien and his co-authors have also done additional work on trying to focus on designing better algorithms for how they turn out on the actual experimental data.
Okay, thank you very much.
Hello everyone, I'm Xueyu Mao. Today I'm going to introduce our recent work overlapping clustering models and one SVM to band them out. This is a joint work with Professor Purnamurthy Sarkar and Professor Dipen Chakrabarty. We all come from UT Austin. So first, let me warm you up with the well-known statistics block model in network analysis. In this model, there are n nodes and k communities in the network. There's a community interconnection matrix B, where each element Bij is a probability that there is an edge between community I and community J. And for each node, there's a cluster membership vector theta I, indicating the community node I is in. And finally, the node interaction probability matrix is simply theta B, theta transpose. And the adjacent matrix is a Bernoulli sample of the probability. This model is well studied, but there are still limitations. First, each node belongs to exactly one community, and also within the same community, all the nodes have the same expected degree because P is like blockwise constant. So some extensions are proposed to deal with these problems. For example, mixed membership block models extended to allow overlap, and the degree correct block models extended to allow heterogeneous degree distributions by assigning a degree parameter gamma I to each node. Note that there are also many other extensions to this model. So our model is, the model we are working on is such an extension, like we allow both degree parameters and we also allow each node to belong to different communities. And this model covers many well-known overlapping clustering models. For example, degree correct mixed membership statistics block model, OCOM, SBM. And also it covers LDA topic model as a special case because we can cast the word co-occurrence matrix into such a form. Note that many fast approval algorithms are proposed for different models. But in this work, we show that we can propose one simple algorithm that works for all these models. And the main idea of our algorithm is to find the extreme rays of a convex cone. This is motivated by the observation that the rows of the eigenvectors of P actually form a cone. This is the algorithm sketch. So first, we normalize the rows of V to unit L2 norm. This eliminates the effect of the degree parameter. And we can see, after the normalization, each node lies on the intersection of the cone and the unit sphere. And we show a very interesting result that if you run a one-class support vector machine, and we can prove that the support vectors are actually the corners. And with these corners, we can simply estimate the community memberships by a regression on these corners. So this illustration is for the simple population version, but we can also show in the paper similar ideas probably work for the empirical version. We show that this one algorithm yields consistent guarantee for community memberships of each node, while most existing algorithms showed guarantee for the whole community membership matrix. And we also show that our guarantee works for all overlapping models mentioned earlier. For example, the per node consistent guarantee for DCMSB is as follows. In this model, the community membership vector theta I comes from a Dirichlet distribution. And we can show that under a broad parameter regime, if the average degree of the network is larger than polylog n, then with high probability, the largest row arrow can be bounded by O tilde J over square root rho n, where O tilde has the polylog n factor. And J is something depends on the model parameters. I will not talk in detail here. And also note that we have similar results for topic models. In conclusion, we propose a simple and scalable algorithm that infers the community membership of each node. for a broad class of overlapping classic models. And we have good performance on several large-scale datasets. If you're interested in more details, please come to our poster next door in 20 minutes. Our number is 114, and it's not on the second floor. Thanks a lot for your attention.
Good morning, everyone. I'm going to present removing the feature coordination effect of multiplicative noise. So multiplicative noise is widely used to regularize deep neural networks. A well-known example of multiplicative noise is dropout. To see that, we can divide the dropout mask by its key probability to obtain the equivalent multiplicative noise. But despite the empirical success of dropout, we identified the side effect of multiplicative noise. So if we apply some noise to the activations of some hidden layer, the pre-activations of the next layer is simply a weighted sum of the noisy activations of the lower layer. We can then decompose the pre-activations into a signal component and a noise component. At training time, to reduce the interference of noise, a simple strategy that can be learned is to increase the signal-to-noise ratio of the pre-activations. If we model the tendency of increasing the SNR of pre-activations as an implicit objective function, we can prove that maximizing the SNR is equivalent to maximizing a form of coordination between the lower layer features. So training a neural net with multiplicative noise tends to increase the coordination between features. To remove the coordination effect, a simple solution is to truncate the gradient through the noise component. But by doing so, maximizing SNR is now equivalent to increasing the magnitude of the signal component, or the variance of the pre-activations. Fortunately, we can apply batch normalization to pre-activations to prevent this tendency. So a better solution here is to combine noise gradient truncation and batch normalization. Based on this idea, we propose non-coordinating multiplicative noise, which decomposes batch-normalized pre-activations and truncates the gradient through the noise component. We also developed two variants based on this idea. The first variant is computationally more efficient and is as simple as dropout in terms of implementation. And the second variant decomposes pre-activations once every 2 layers, which we find to work better on residual networks. And this variant can be seen as a simplified version of shake-shake regularization that doesn't require extra residual branches. And we show that this connection also explains why shake-shake regularization works. In experiments, we observe significantly reduced feature coordinations, and the resulting coordination level is even lower than the baseline without noise injection. And this is observed both on plain convolutional neural networks and residual networks. The classification accuracies on CIFAR 10 and 100 are also improved. In particular, on residual networks, the performance gain is more than tripled compared to standard multiplicative noise or dropout. We also show consistent performance across different architectures and different network sizes. And we obtain almost the same accuracies compared to shake-shake regularization, but in 9 times less training epochs. To conclude, we identified the feature coordination effect of multiplicative noise and developed non-coordinating multiplicative noise as a better alternative to drop out for batch normalized neural networks. For more details, welcome to our poster 107. Thank you.
Hello everyone, this is Hu Liu from Tsinghua University. My work is connectionist temporal classification with maximum entropy regularization, and this is a joint work with Sheng Jin and Professor Changshui Zhang. Connectionist temporal classification is an objective function for end-to-end sequence learning. End-to-end, for example, in this picture, we label the picture with a word, but we do not label the position of each letter. CDC gets the end-to-end model training by maximizing the sum probability of all feasible passes. However, as the number of feasible passes grow exponentially as the sequence length, it is difficult for CDC to find the most suitable path, which means that the model may learn the sequence in correct order, but at wrong positions. And positive feedback like error signal of CDC just aggravate this problem. To summarize, CDC has 3 drawbacks. CDC lacks exploration and is prone to fall into worse local minimum. CDC outputs overconfident passes, and CDC outputs passes with picky distribution. We give 2 solutions to handle these CDC drawbacks. Our first solution is the maximum conditional entropy regularization for CDC, the EN-CDC. Also, in this example, the first line is the CDC prediction with picky distribution, and the second line is our expected prediction with correct segmentation and ambiguous segmentation boundaries here. You can see that the expected prediction has a higher entropy. Based on this phenomenon, we add the entropy-based regularization to the CDC loss. This is the EN-CDC. EN-CDC have several benefits. The first benefit is EN-CDC can alleviate the CDC's positive feedback like error signal and get better generalization and exploration. EN-CDC can solve picky distribution problem of CDC. EN-CDC can depict ambiguous segmentation boundaries. Our second solution is that eco-spacing CDC. We call this ES-CDC. The fundamental reason why CDC is difficult to find a suitable path is that there are too many feasible paths. What if we can reduce the number of feasible paths without the loss of accuracy? We observed that the spacing of 2 consecutive elements is nearly the same in many sequential tasks. For example, the third line with eco-spacing is more reasonable than the first line and the second line. We adopt eco-spacing as a pruning method to rule out unreasonable CDC paths. This protects our model from distractions, and we have fast convergence. Also, we give a theorem that links the eco-spacing and the maximum entropy, which indicates that eco-spacing is the best prior without any subjective assumptions. We give dynamic programming algorithms for EN-CDC, ES-CDC, and EN-ES-CDC here. The qualitative analysis shows that our algorithms have better error signal in training, and we provide better alignment. The results on syntax recognition benchmark show that our model have better generalization on the small data set here. And on the large data set, our model outperforms the CDC model with no edit to the training settings. For more results and analysis, please come to our poster. Thanks.
Hello, everyone. In this work, we present a formula inspired by statistical physics to compute mutual informations and entropies in models of deep neural networks. Recently, information theoretic ideas have been receiving rising interest in the deep learning community, either as a tool to understand the generalization ability of commonly used training algorithms, or to design new regularizers. Typically, one wants to compute the mutual information between the inputs of a neural network and its output, or any of the hidden representations. But in a stochastic deep neural network, the probability distribution of a given layer is generally intractable, and computing mutual informations, or closely related entropies, is yet more involved. Using samples, non-parametric estimators, and variational methods are interesting strategies, but they are likely to become less and less accurate as the dimension of the layers increases, and benchmark cases where controlled estimates are possible are needed. In this work, we take a different approach and restrict to a class of models of deep neural networks to propose an estimator that is based on the replica methods from statistical physics. So the model is the following. We consider a fully connected stochastic feed-forward neural network with two main assumptions. First, that the input distribution is known and that it's factorized over the components. And second, that the weight matrices are drawn from a certain class of random matrices. While it starts to have quite a few results in the literature around IID Gaussian weight matrices, we here consider the even larger class of orthogonally invariant matrices, meaning that for the weight matrices of the entire network, in their singular value decomposition, the orthogonal matrices are drawn independently from the R measure, while the diagonal matrix is arbitrary and can be learned. With this class of models, the replica method allows to derive heuristically the entropy at the else layer in the limit of infinitely wide neural networks as the minimum among the extrema of a potential. The potential is apparently complicated, but it's actually easily evaluated as a sum over layers of entropies and mutual informations of scalar variables. We make publicly available an efficient implementation of the extremization of the potential. And secondly, we provide a proof that for the case of two-layer neural networks with IID Gaussian matrices, then the replica prediction is exact. And as an application, we demonstrate that the formula can be used to study the training of neural networks by proposing the following experimental framework. From an IID latent representation, we use a generative model with fixed random weights to generate input data X with a non-trivial distribution, and an arbitrary teacher rule to generate corresponding labels. We can then train a student network on the corresponding task of recovering Y from X using the synthetic dataset. To guarantee the orthogonal invariance of the weights during learning, after the initialization of the weights, we only update the spectrum, that is the entries in the diagonal matrix, and we are doing so using propagation. As a result, the entropy in the Markov chain running from the latent distribution, and in particular in the students, can be computed with the replica methods at any stage of learning, and we can report trajectories in terms of information of any learning algorithm, such as, for example, SGD. For example, here we construct a binary classification, and we ask how a 5-layer deep student would learn it. And we can, for example, follow the mutual information between the input layer and the fourth hidden layer. And we can repeat this experiment, varying settings, varying learning algorithms, or varying students. So for example, here with different nonlinearities or different initializations on the exact same task. And if you are curious about it and you want to know more, our poster is 110. Thank you.
Hi, my name is Benjamin Aubin. I will present you our work on computational gaps in two-layer neural networks. The goal here is to understand if we can efficiently learn a teacher neural network from a limited number of samples. To do so, we use a theoretical approach based on a typical case teacher-student scenario, and we consider a two-layer fully connected network with fixed weight on the second layer, called a committee machine. On one side, we fed the teacher network with IID random samples that generates the output Y star. On the other side, we have a student network with the same architecture and he wants to learn the W star knowing the training set provided by the teacher. The aim here is to analyze if this learning task is possible and to evaluate the corresponding computational complexity. The traditional approach to tackle this question is based either on worst-case scenario or pack bounds or numerical experiments. Instead, we revisit the statistical physics random case for IID data coming from a probabilistic model that allows us to analyze theoretically the generalization performances of neural networks. Let me emphasize that our results are correct in the infinite input size limit, and that we consider a ratio between the number of samples and this input size of order 1. Our main result is about the generalization error in the base optimal case. In the infinite input size limit, we provide an explicit formula for the generalization error that depends on the parameter Q star. This parameter is called the overlap in physics, and it measures the correlation between student and teacher weights. And in fact, this parameter can be computed using the replica mutual information as a critical point of this replica mutual information. And note that this kind of heuristic replica mutual information are well known in statistical physics since the 80s, but our main contribution is to provide a rigorous proof of this formula using adaptive Guerra interpolation. Our second main contribution is the design of a message passing algorithm. While trendy algorithms consist in minimizing a loss function, which is not optimal for a limited number of samples, we provide an approximate message passing algorithm, which is structurally different. It derives from the expansion of belief propagation equations on a factor graph and can be written as a closed set of iterative equations. And instead minimizing a loss function, it estimates the marginal probabilities of the weights. So the main benefits of this algorithm are first, it's conjectured to be optimal among polynomial algorithms in many cases, and second, it can be tracked rigorously using the replica mutual information. Okay. To illustrate, I will show you the result for Gaussian weights, sign activation functions, and for a large number of hidden units K. And we compare the base optimal generalization error with the generalization error performed by the IMP algorithm. For a small number of samples, the IMP algorithm follows exactly the optimal solution, and in this regime, the optimal solution has non-specialized hidden units, meaning that hidden units are equivalent. At this point, we observe a discontinuous specialization transition at which the optimal solution jumps and then decreases to 0. In fact, this jump is closely related to the fact that in this regime, the symmetry between hidden units is now broken. And so we have a specialized hidden units regime. However, the IMP algorithm does not follow the optimal solution anymore, and it remains stuck in the non-specialized plateau with high generalization error. And in fact, because of the existence of this local stable minima, it remains stuck in this solution, and it remains stuck for a number of samples scaling at least with chi-square. So it highlights a huge computational gap between what is theoretically achievable and what the best conjectured polynomial algorithm performs. So if you want to know more, you are welcome to come at our poster number 111. Thank you.
Thank you for joining us. This concludes the session for today. I encourage you, if you have questions, to come up and meet any of the speakers. They're all up in the front here, or attend their posters. Again, thank you for coming.